Good morning from New York City, or is it afternoon? Afternoon. Anyway, it's a nice, fine autumn day outside. Good day for riding the motorcycle up to Dobbs Ferry. Anyway, I want to continue now with a closer look at relativistic quantum mechanics. Let me say that again. I want to look at relativistic quantum mechanics. Now, as a prerequisite for this, you guys, I've actually used relativistic quantum mechanics before. When I did find structure constant 1, and I worked out the energy levels in the hydrogen atom, I forget exactly what it was. Something like that. It might not have been squared. In fact, I don't think it was. But anyway, you can go back and check that formula. Now then, this is the spectrum. These are the principal energy levels in the hydrogen atom. The first correction can come from spin, whatever that is. The second correction can come from a relativistic effect. And I use the equation that I'm going to use today in that second lecture, or was it? No, lecture 4A. So to catch up with all of this stuff, although a lot of this stuff is not relevant, you can get away with it without looking at any of these lectures, but just for interest, watch find structure constant 1, 2, 3, 4A is the most relevant one. Relativistic correction to the hydrogen spectrum. I actually used the formula that I'm going to derive today. I'm going to derive the Klein Gordon Equation. And then 4B. So that's the prerequisites there. Well, not prerequisites, but you might want to have a look at them because they're entertaining. So, what we're doing today is relativistic quantum mechanics. And we're going to derive now the Klein Gordon equation is relativistic insofar as it is Lorentz invariant, Lorentz covariant, but it has a problem. The solution to the Klein Gordon equation turns out to be a scalar field. Now, if you want to talk about the electron has an extra degree of freedom called intrinsic spin, and the Klein Gordon equation doesn't have it in it. So, to talk about the electron in a relativistic sense, you have to move away from the Klein Gordon equation. Actually, you essentially get the square root of the Klein Gordon equation, and out of that comes what's called the Dirac equation. Now, we don't have time to do the Dirac equation in this lecture. We've just got time to do the Klein Gordon. Anyway, it's enough for you guys to take in. Let me go over the background before I do anything else. Everything to do with this is related to this extra degree of freedom that an electron has called spin. Now, if you want to specify an electron, you need to look at its degrees of freedom, which are spatial, x, y, and z, or it could be r, theta, and phi. But when you get on top of the electron, look at it itself, it has another degree of freedom in the x, y, and z direction, the internal spin of the electron. Nobody quite knows what it is. It can be described in terms of angular momentum, and we'll have to look at angular momentum in a big way. So actually what we'll do is we'll go and look at Laplace's equation, because this surrounds Laplace's equation. Because the eigenvalues of the Laplace operator on its eigenfunction are L times L plus 1, where L is an integer. Now for the spin of an electron, S times S plus 1 is going to be the eigenvalue, but it'll be a half integer. It'll actually be a half for the electron. Some other particles will have other half integers. And such particles that have half integer spins will be fermions, and integer spins will be bosons. Whatever they are. We're just looking at the Klein Gordon equation. Tidy up the board a bit. So the first person who's heavily involved with the understanding of spin at the early part of this century is Wolfgang Pauli from Vienna, 1900 to 1958. spin. So we will actually derive the Pauli equation, or at least we'll write it down and talk about it, after Wolfgang Pauli. He died in 1958, died prematurely. He had palsy. He was a very funny guy. Look up Pauli quotes on the web. So Wolfgang Pauli overshadows all of this stuff, right? Wolfgang Pauli was the oracle. Rather than have many famous papers out, and he has a few, he's in papers, he's in everything, because he was the oracle. People would consult him before moving ahead, or to find out something. Wolfgang Pauli. He was a bit blunt. Other participants, William Clifford. Dirac came out with his relativistic equation in 1928. Paul Adrian Morris Dirac. Now, it turned out that the matrices inside the Dirac equation obeyed what's called the Clifford algebra. Invented by William Clifford in England, King's College, my old college, 1845 to 1879, once again died prematurely. William Clifford, Clifford algebra. And of course Dirac, 1902 to 1984. And in the Proceedings of the Royal Society, 1928, he came out with the famous paper on his relativistic quantum mechanics. He just guessed at it, by the way. It's kind of hard to derive it. In fact, when I looked at trying to derive it, taking the square root of the Klein Gordon equation, not really deriving it, right? You have to guess at the structure of it. So, the Klein Gordon equation, W. Gordon, Journal or Zeitschrift for Physics, 1926, and Oscar Klein, 1926, also a later journal, slightly later. Actually, no, this is later, volume 40, this is volume 27, so he came first. That's Oscar Klein of Kaluza Klein and Klein Bottle and a whole lot of other Klein things. I think also scalar theories of gravity was Oscar Klein. Now, behind this is the infrastructure of Eli Cartan, the language of spinners. The algebra of spinners was invented by Eli Cartan in 1913. Eli Cartan wasn't recognized in his own life. He wasn't recognized until he was much older, 80s or something like that. And he was recognized by the great Poincaré. And it took only a clever guy to recognize another one. Eli Cartan was French. Spinners. So that's the background for this. And now we'll do the Klein Gordon equation. First of all, I'll remind you of the Schrödinger equation. Schrödinger equation is this. Is that the Schrödinger equation? Not quite. It will be when I make these operators and have them all operate on the wave function. The wave function, which is interpreted by Max Born and a few others to be the probability amplitude of finding an electron somewhere. Now, why p squared over 2m? It's just a rearrangement of the kinetic energy formula. This is the kinetic energy, this is the potential energy, and this is the energy operator. So let's see what that looks like. Well, the momentum operator is minus IH cross d by dx, or using nabla in 3 dimensions. Nabla can be in Cartesians. Nabla can be in polars. This basically is if I just set this to 0, that's basically the Laplace equation. And you solve the Laplace equation and you get eigenfunctions of angular momentum. Okay, so what's p squared? I'll stay in 3 dimensions now because you know you can easily go to 1. So minus 1 squared is plus 1, I squared is minus 1, and h cross squared del squared. we'll now look at E squared. Even though E squared doesn't show up in here, I'm going to get it for us. So that's what E squared is, and this is going to be the Schrodinger equation, so let's put that in. Now we notice straight away that this is second order in the derivative, and this is first order in the derivative, and that's the big difference between the Klein Gordon equation and what the Schrodinger equation is. I don't need this stuff now. I'm just going to carry what I do need. I need E squared and P squared. Okay? So I get all this off the board. Now in special relativity we have the well-known result. You say, well-known result? You have to know this. It's a prerequisite for doing a lot of these lectures. I didn't give a detailed lecture on special relativity because other people are doing it all over the place. What I do is, if I give a talk, I give it because I have my own way of looking at things, which is usually a simplified version. When you get stupid, you have to simplify things for yourself. Other things I have are ideas which nobody else seems to think about. I do those kind of lectures. Or sometimes my son asks me to do something. For example, he wanted to do organic chemistry one time, and I did a lecture on high school organic chemistry. Things like that crop up if my kids ask, or if a person in the audience, and you guys, have asked me questions certain times. I've been asked questions, and I do a whole talk which answers those questions. Or I might answer them inadvertently when I'm talking about something else. Sometimes I go ahead and do things systematically. I started doing college lectures in physics. If I go back teaching in college next term, then you'll get a whole college course, maybe 2 or 3. We'll see, down in Florida. So, in relativity, special relativity, now unfortunately some of the mathematicians have ruined special relativity. Old special relativity was dead simple, right? They started talking about, 4 vectors and so on and so forth. I can't be bothered with them. Just learn ordinary relativity first. Well, we take that equation and we'll use common sense. What are we going to do? We want to quantize this equation. What did we do for the Schrodinger equation? We made the dynamic variables operators. So let's do that. Here's another one. I don't know if that's classified as one, but it's a constant. A constant can still be an operator. Now they have to have something else. What did we do in the Schrodinger equation? We introduced the wave function. So we'll introduce one for these guys as well. Phi of x of t. We'll just call this one phi because we've already used up a psi. Now we put in for our operators, e squared. Now Now sometimes theorists put in h cross equals 1, c equals 1, but I don't do that. I just go m becomes m dash. Right? We'll talk about that later. Because you actually lose information. What we want to do is keep information. You lose information when you throw away your constants. So they all act on the phi of x. We'll remember that. So we don't have to keep putting in the phi. We'll just remember that phi of x of t is the scalar function, which is going to be a solution to this equation. Now we're going to divide across by minus Now I made a mistake here. Or did I? This had to have a c associated with it. Okay? All right, now we're correct. Now I could equally divide across by positive h cross squared c squared, in which case I would get a whole different signed equation. I'm going to talk about signature of a metric in a minute. So let's rewrite the equation now that we have adjusted. Well, the h crosses cancel. And the sign gives me a 1 here, and I get p squared should be c squared, c squared. You have to watch me sometimes. I make these silly mistakes. C's cancel, or do they? Yeah. This is a minus. Don't forget it was a minus we divided by. C to the fourth. C to the fourth. Now you guys know that these are operating on the phi, so I leave out the phi for the moment until I have everything under control. What I want to do is bring everything on the one side. So I'm going to bring this over here, and then everything will become 0. Now this will be our Klein Gordon equation. We use this to get this. So I bring it up here, and I bring this operator over here. I'm just calling this m dash squared, m c squared over h cross squared. I'm not choosing units of c equals 1 and h equals 1. Now straight away we recognize this guy here, and we have a minus sign here. I could equally well have made this a positive sign. Remember when I was deriving, I derived by negative. I'm just keeping this version of the Klein Gordon equation. Could be positive. But that would mean I would have to look at the signature of this guy, which is now known as the wave operator. Separating phi. And that's a form of the Klein Gordon equation. Let's look at this operator now. Now, remember, at least learn that another way to write the derivative with respect to x is this shorthand way of doing it. All right? So I want to rewrite this equation now. Like this. What will I put in here? The matrix necessary to give me this form. Right? And I put in the rest of the elements. Yes? Now, this is the metric of special relativity. If I had used the positive sign here, I would have had to have negatives, 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 and positive here. In other words, what's called changing the signature of the metric. But I'm using this convention. And for that reason, I have to keep the negative in the m squared. Okay? This I'm going to say, in terms of tensor components, can be written like that. That is another way of writing the block, where we sum over the mu's and the nu's according to the Einstein summation convention, which I taught early on in my general relativity classes and special relativity. If you want to learn about that, go back and look at those classes. I never used the sigma sign. Okay, this also has the effect of raising one of either of those indices. Now we have got our result. So I'm just going to write down the Klein Gordon equation in the two most familiar ways that you see it. This is, in fact, a Klein Gordon equation. So is this, so is this, so is this, and so is this. But to keep the board simple, we'll do this. These are the two simplest ways that people remember it. Both are the same. The block operator contains the nabla in here and the time derivative as well. Now straight away we see that we have time and space on equal footing. That is the Klein Gordon equation, and it is relativistically covariant. After this comes the Dirac equation, and that's a long lecture, okay? Actually, I'll do the Dirac equation, but I will also do Pauli, the Pauli spin matrices as well. Whole lecture coming up. I haven't decided which is coming up. I guess I'm going to have to do angular momentum first. Anyway, I might just launch straight into the Dirac equation, then go back to angular momentum. All right, see you later.